Hi there, everybody. Robert here, and what I wanted to do is I want to make a quick video on some stuff involving the derivative. These are for the students who are in Mrs. Ramos's class, and as everybody probably knows, Mrs. Ramos doesn't know shit about math, so she's probably wondering what the fuck is going on herself. Um, I'm pretty much guessing that everybody's laughing when I say that. So right now in class, you guys are going to be looking at a test that's coming up. And you guys are looking at something called the derivative. And what the derivative is, it's a way of finding the value of a slope at a specific point on a function. So if this was function f of x, and if this is just some value a, then at this point a, the tangent line right here will have a slope. And the slope of the tangent line is known as the derivative of the function f at the value of a. This guy gives us a particular number. Another way that we can describe the derivative is a function itself. Like if I wanted to just keep everything general and leave this point as just a variable, then if this function was f of x, and if I wanted to find the slope in general at any single point, then I would find a function called f prime of x, known as the derivative function. Okay? Just for an example, suppose that your function was x squared. It gives you this parabola right here. We can kind of pick like 3 points. Here's one that has a slope that's negative. At the vertex, the slope is 0. At the vertex, that x coordinate is 0. Let's just say that this x coordinate is like -2. And then over here, at an x coordinate of +2, the slope seems to be positive. If we did the derivative using the power rule or the limit notation, we would find that the derivative as a function is 2x. And here, we could say, hey, what is f prime of -2? It's -4. Or what's f prime at 0? It's 0. Notice that -4 is this negatively sloped line. 0 is this zero slope line. If we did the derivative at +2, we get a +4. So what the derivative, again, it tells us the slope at any point along the function that the derivative came from. The difference in notation, when you do the derivative at a point, you are finding the derivative f prime evaluated at a, where x is equal to some value. And there's one thing called the limit definition. So the limit definition of the difference quotient, that's the standard expression that you guys usually deal with. So it's the limit as h goes to 0 of the function at a plus h minus the function at a all over h. What that is a secant line that's created over at some value of a plus h. And the secant line slope is actually greater than the slope of the tangent. But when you let h go to 0, what happens is that this secant line, if I can go ahead and draw it again, let's just say here's our tangent line, and then here's our secant line. H is this interval right here. And if h were to shrink down, this point would actually migrate over here. And then you draw a new secant line. And notice that this new secant line is a little greater than our tangent line, but not as great as our original secant line. And as h goes to 0, the secant expression, the slope of the secant, becomes the tangent line, or the slope of the tangent. Okay? So that is one expression right here, the limit definition of the difference quotient. Usually teachers will particularly say, hey, find the limit or find the derivative of the function at this point using the limit definition of the difference quotient. If you have a good teacher like Cass or well, that's it. Kawasaki is meh, and Donner, I don't think she teaches this anymore. Cass would specifically say use this expression. This is just going to give you a number. Okay. Another way that you can find the derivative at a point is using the limit of the average rate of change. So if you remember, the average rate of change on an interval was the function at one value minus the function at another value over the difference of those two values. And here, what you're going to do is you're going to take the limit as x approaches a. Okay? This is also going to give you the same number that this guy's going to give you. Sometimes this expression is easier to do, especially with polynomials. So then we deal with, all right, what's the method of how to find the derivative as a function? So when we take the derivative as a function, we can only use the limit definition of the difference quotient. The reason being is we want to leave the expression that has variables left. So we have this limit as h goes to 0. We have this f of x plus h minus f of x all over h. And this is going to give us an actual function. A function which has x's and shit, so x's and shit, to plug in, okay? So what I want to do is let's just go through a doozy. F of x is x squared. Let's find the derivative as a function using the limit definition, and then let's also find the derivative at 2, which we know it's going to be 4, but let's find that by using both limit definitions. Okay, so if we're trying to find the derivative f prime, it's the limit as h goes to 0, and we're going to evaluate f at x plus h minus the function at f of x minus the function f of x all over h. And from here we plug in x plus h into the function. It's just so we have this limit. Don't forget that. We plug in x plus h in for x squared. Then we subtract the original function, and then we divide by h. And what we have to do here, in general, for polynomials, we generally expand them and then see if we can drop out the original terms. If we FOIL x plus h squared out, we'll have an x squared, a 2xh, and an h squared. And then you have the x squared, which drops out here and here. On the bottom, we have an h. I like to show the extra step. And so notice we'd factor the h out on the top. There's a 2x plus h on the top and h on the bottom. Those guys drop out. And then we have this limit as h goes to 0 of 2x plus h. Our limit is clear to plug in 0 because we didn't want to plug in 0 before when we had an h on the bottom here, or here, or here, or even here until it dropped out. Once you dump in 0, we just get 2x. Cool, awesome, pretty easy, right? So for polynomials, that's the deal. Now, what if I wanted to find the derivative? So really quick, if I take the derivative at 2, I would plug in 2 into the derivative, and I know on my parabola at an x value of 2, I would have a line that has a slope of 4. Okay. What if I wanted to find the derivative at 2 using the limit definition? I would take the limit as h goes to 0, and I would write my function at 2 plus h, not x plus h, minus the function at 2 all over h. Okay, and then what you do is you run through the algebra again. If you plug in 2 plus h into the function, it's 2 plus h quantity squared. If you plug in 2 to the function, it's just 2 squared, and this is all over h. You just rock on with the algebra, get it all simplified. You have a 4 plus 4h plus h squared minus a 4, so notice that the 4's drop out, and divided by an h. I would show the extra step, but you guys can follow from the other one. So one of the h's drop out everywhere. So now you have this limit as h goes to 0 of a 4 plus h. And if you plug in 0 for h, it just becomes a 4. Cool. Notice that those guys are the same. And then let's just do the last one really quick to just show that we would get the same shit. Let's see, cut. All right, so then if I wanted to find the derivative using the limit of the average rate of change, I would write that as the limit of h goes to 0, sorry, the limit as x goes to 2 of the function at x minus the function at 2 over x minus 2. So we have this limit as x goes to 2, the original function's x squared. If we plug in 2, we get a 2 squared, and we have an x minus 2. And we continue with this limit. We have an x squared minus 4 on the top over an x minus 2. And what usually happens is this factor has to appear, if we're dealing with a polynomial on the top, it should appear on the top. If you can't factor it correctly, you fucked up and did something wrong. So here we have an x plus 2 and an x minus 2 on the top. That's just a difference of squares. We have an x minus 2 on the bottom. Those guys drop out, and we're safe to plug in the limit. If we do the limit as x approaches 2 of x plus 2, we just plug in 2, and we get a 4. And that's it. What I would highly recommend on the test, if you guys really feel weak on your algebra, is just do the derivative the standard way, like the power rule way. So if your function was like x cubed plus 3x squared minus 7x plus 2, and you had to find the derivative at like 4, just really quickly do the derivative using the power rule. And so it would be a 3x squared plus a 6x minus 7, and then plug that in and just see what 4 gives you. It's going to give you some number, okay? And then when you actually do the derivative at 4 using like the limit definition and plugging in all your x plus h crap and blah blah blah, you know that if you make a mistake and if you don't get this number that you were supposed to get here from, let's see, there he is. If you don't get this number that matches what you're doing here, then you did something wrong. So anyways, I hope that helps, and I might as well go ahead and throw in a couple other things. So you guys are only going to be dealing with polynomials, so polynomials, rational functions, and functions with radicals. When you're calculating the derivative using the limit notation, for polynomials it's quite easy. When we had that limit as h goes to 0 of, if we did x squared, we'd have an x plus h squared minus an x squared over h. What you usually do is you expand the top and then you eliminate stuff. Eliminate crap, stuff that drops out, and then usually the h should drop out on the top and bottom. If it doesn't, you did something wrong. Algebraically, something went up, okay? For a rational expression, like if you were doing the derivative of 1 over x, your expression would look like this. You'd have a 1 over x plus h, because that's a function at x plus h, minus 1 over x over h. This is something called a complex fraction. And a complex fraction, the thing that you want to do is you want to clear the denominators. So I'll just put denoms. So what you'd want to do is you take this 1 over x plus h minus 1 over x over h, and you want to clear both x plus h and h in the denominators. So you multiply x and x plus h on the top, but you do the same thing on the bottom because you're technically multiplying by 1. When you do that, this limit you're doing is h going to 0. You do not want to distribute the bottom. You're hoping, what we're doing is we're hoping that this shit drops out. So on the bottom, you should just have h, x, x plus h. On the top, when you distribute this expression to both terms, you'll have this. Just be careful of your signs. You should end up with a negative h on the top, and then this hx, x plus h, just for this particular problem. Notice the h's drop out. Then you're good to go, okay? The last part for radicals, if I had the square root of x, your derivative would look something like this if you did the limit notation. It'd be the root of x plus h minus the root of x over h. When you have radicals, you want to rationalize the numerator. You want to basically multiply by its conjugate, okay? So when you multiply by its conjugate, you multiply by the root of x plus h and the root of x with a plus sign, basically the opposite of the sign between the original expression. Again, you leave the bottom alone. You leave it factored as an h, the root of x plus h, and the root of x. On the top, when you FOIL it out, the roots drop out. You have a difference of the difference of squares that kind of comes out. You have an x plus h and a minus x. And notice that those x's drop out, and look at that, our h's drop out. So you'd be left with a 1 over, the crap on the bottom. So a lot of algebra is involved in simplifying these expressions, but once you can identify what type of derivative that you're doing, you should be good to go. So I hope that helps everybody, and I want to wish you all good luck on the test. And in the future, if you guys need any help, hit me up on this little video. Leave a comment. I'll talk to you later. Take care.